So you see that we can call flush, but if you don't call flush, then there's some automatic flushes that happen. And the picture I drew before was block buffered. When the buffer that's inside a file pointer got full, then the bytes were flushed by making the system call to actually write them to the kernel level pipe. You can set a file pointer to be unbuffered mode, and that means every fwrite acts like a kernel write. It goes through the kernel every time. So you don't usually want to do that for performance reasons, but you might want to do it for concurrency reasons, to actually have the bytes go out to the device. There's one more possibility, which is line buffered, and that is flushing not because the buffer is full necessarily, although it will do that if the buffer gets full, but also flushing whenever there's a carriage return or new line, actually a new line in the output. That's why when we write programs, we need to put a new line on them to actually see the printout if there's some sleep or something else happening in between. Right? So that's why it's a good practice when you're using printfs to just test things out and see where you are in the program. That's why you need a \n in it. It's because the default mode tends to be line buffered, and hello without a new line will just stay in the buffer without going out. Right? The default buffer mode is actually kind of complicated. Standard error is set by default to unbuffered mode. The idea is if you have an error, you want to see that information right away, no matter what happens next. Like if it's going to print, I'm about to deadlock, and then it freezes, you want to actually see the information that it's about to freeze. When the output that is standard out or some other file descriptor that you open explicitly, when that is a terminal, then line buffered is the default. And the C library figures that out because the kernel provides a call is a TTY, which means is it a terminal? And so when a particular stream, wherever it came from, when that file refers to a terminal, then the default buffering mode is line buffered. Otherwise, if you open a file, then it's block buffered. And in particular, if you use the shell to redirect the output of a process to a file, then that output will be block buffered instead of line buffered as it would be if you ran the program directly. That's why programs sometimes behave differently when you run them with the output going to a terminal and going to a file. And that can be confusing, but it comes down to the difference in the default block buffering modes, and the reason the default works that way is for efficiency. And when you're writing to a terminal, the idea is you want to see it right away. When you're writing to a file or to another process that might be a pipe connection, then the idea is you want to stream bytes through as efficiently as possible. Beware of the default buffering modes and that effect in your program. So stepping back a little to summarize, we have a couple of I/O options when you write C programs on Unix. You can use the system level Unix I/O. That's designed not so much to be used directly, but to expose the minimal functionality that the kernel needs to provide. So you get all the control that you can have, but it's slow for small transfers. Also, you have to deal with the possibility of partial reads and writes, and we've only talked about that a little bit, but we'll talk about it a little more when we get to signals. Standard C library provides better performance generally by using buffers in an appropriately and usually appropriate default way. It also provides many convenience functions like printf that we used before. There's fprintf where you actually give it the file star that you want to write to. Printf is just the same as fprintf using standard out. On the other hand, you get a little bit less control because it is standard and not all OSs provide the same capabilities. So not everything maybe is visible through the standard C library. In fact, there are many, many other I/O options. There are many other libraries other than the standard C library. In this class, we have a couple of more even from the csapp.c. There's an SIO API, which takes the Unix I/O API and just adds a few convenience functions. Kind of printf-like, but not as sophisticated. You should read the book to see about those, or csapp.h, and I'll just use them without commenting on them more. Later we'll also look at RIO, which again wraps Unix I/O, but instead of convenience, its aim is to deal with the partial reads and writes for you automatically. Again, neither of those solve the slow for small transfers if that's an issue, so using standard C library is the way to solve that kind of problem.